Award in biomechanics, so exists since 2012, and the criteria of evaluation who are available online, if you go to the ESB webpage, so are the capacity and knowledge gap, the approach, so methodology, the research output, so kind of results, novelty of results, publications, etc. And very importantly, the European dimension. So we're a European society. We're really looking forward then the researchers then to move across Europe, because that's the way we really the European dimension of research. So we have, in the evaluation review, we have 5 independent reviewers, and we go through several rounds of review. So we have a lot of information to evaluate. So I would like to acknowledge then the reviewers that have done very hard work in reviewing all the applications we've received this year. So indeed this year we've received 14 applications, so 14 PhD theses, and although we have one winner, it was very nice to see that the level was very high. So even those PhD theses who have not been selected for the awards had already a very high scientific standard. So it's really pleasant to see that, and it really shows that we're a strong scientific community, we're a strong scientific level. And so we had one winner, so Lorenzo, and we had 2 runners-up. So at the Congress Gala, so we will present the runners-up, who were 2 other awarded persons for the quality of their PhD thesis. So Lorenzo did his biomechanical engineering degree at the University of Pisa, and then in Italy. Then he worked at the Rizzoli Institute, so in Italy, and then he moved to Sweden, where he did his PhD study at the biomedical engineering department at Lund University. And he is indeed now a postdoc. He has done the military service. Yeah. And so he's working on subject-specific femoral finite element model for the assessment of risk fracture, so in the continuity of the PhD thesis. And so now he will present then his work, which is called Femoral Strength Prediction using finite element model. So, Lorenzo.
Thank you, Jerome, for the introduction. I'm very happy to have the chance to present my thesis in front of you today. And I'm just reading again the full title since I gave a short one. It's Femoral Strength Prediction using Finite Element Models, Validation of Models based on CT and Reconstructed DEXA Images against Full-Field Measurements. So I defended my thesis in November 2016 with Professor Mark Taylor from Flinders University as the faculty opponent. And I'm here quickly recapping also the European dimension of the thesis in a way. So as Jerome said, I'm originally Italian, and I studied in Pisa. And after that, I moved to Bologna, where I spent 3 years, and I basically started to love biomechanics and research in general. So then I decided to go to Lund in Sweden to get my PhD hat. And to give a bit more of European dimension to this, I had the chance during my PhD project to visit 2 other research places, namely the Technical University of Delft in the Netherlands and the University of Eastern Finland in Kuopio, in the eastern part of Finland. And just a short mention about our group. At the moment, we have 2 principal investigators. We have 3 postdocs, one of which is me, since I decided to stay over in that place, 2 affiliated researchers, 4 PhD students, and 1 master's student at the moment, since summer break is approaching and everyone wanted to present and go away. So a more scientifically interesting way to have a look at map of Europe is not to have a look at my career path, but actually to have a look at the hip fracture incidence map. And it's quite clear from the picture that pretty much all Europe is either in the yellow or the red region, which means from medium to high incidence of hip fracture. And hip fractures are a quite common problem, with 1 in 6 women over age 50 who is nowadays expected to experience a hip fracture during their lifetime. And the consequences of hip fracture can be dramatic, with 40% of the subjects who do not recover and are not able to walk independently at 1 year after the fracture, and studies reporting that at least 20% of the subjects die within 1 year after the fracture, and that's mostly due to the complications which are associated with the treatment and the hospitalization of the patient. So this high number of hip fractures is normally associated to osteoporosis, which is a disease of bone which results in bone loss. And as a final consequence, the bone gets brittle, and the patients can experience a fracture with just a minimal trauma, such as, for example, a fall from a standing height. And for this reason, they're called fragility fractures. The diagnosis of osteoporosis is done using a device called dual energy X-ray absorptiometry, or DEXA, as it's normally referred to. And this device can basically take a calibrated X-ray image from which the bone density can be calculated in a certain area. This density is then compared to the bone mineral density of a young, healthy woman of the same population group, and if the difference is below 2.5 standard deviation, then the patient is classified as being osteoporotic. So what happens when you're osteoporotic? Well, normally you get a pharmacological treatment, which consists of drugs like bisphosphonates, whose main effect is to slow down the bone resorption process. So for this type of treatment to be really effective, we actually need to catch those subjects who are at risk for fracture in time and with good accuracy. And for quite a long time, the people at high risk of fracture were considered to be those who have osteoporosis simply. And while it is true that people with osteoporosis have a high risk of fracture, there is also 50% of women and 70% of men who experience a fragility fracture without meeting the requirements for the diagnosis of osteoporosis. So in order to account for this, more complicated methods have been developed in which the information from the bone mineral density has been combined with some epidemiological parameters, such as a previous history of fracture, smoking, drugs, alcohol consumption, etc., in order to get a better prediction. However, even with these methods, studies are reporting at least 30% of the people who experience a fracture without being diagnosed to be at risk. And one of the reasons for this could be that this type of methods are only capturing a part of the problem, where we can claim that the actual health status of the bone is given not by the bone mineral density itself, but how strong is that bone. And that can be seen as a combination of the density of the bone, how big is the bone and what's the shape, and the different loading conditions to which the bone is subjected. It is therefore not surprising that finite element models are able to predict the strength of the bone better than what methods based on DEXA can do. And this was already shown in 1999 by a study by Cody and collaborators. So that's nothing new in a way. So why are we not using finite element models then? Well, there are several reasons, one of which is that to build a three-dimensional finite element model, you normally need a CT scan, which has the advantage of providing volumetric measurements and the shape of the bone, but also has a few downsides, namely the fact that you have a higher radiation dose given to the patients, and you have higher costs for the healthcare systems. So as a result, the majority of the screening for fracture risk and osteoporosis is nowadays performed with DEXA. So the idea behind this project is basically, can we build a three-dimensional finite element model based on one single DEXA image? And to do this, we can use statistical models. So these models are based on a previous knowledge of the variability of the anatomy of a femur, in this case, a human femur, within a certain population. So if you have a look, for example, at a statistical shape model, that's a model where you put as an input the anatomy of a population of femurs, and as a result, you can describe all the anatomies in this population as given by the average shape for this population, plus a linear combination of the principal modes of variation within that population. And in the same model, in the same way, you can build a statistical appearance model in which you map how variable is the distribution of the bone density for a population of bone. And when you combine these two methods together, you get what we call the statistical shape and appearance model, which I will call SAM in the remaining of this presentation. So how do we reconstruct the 3D shape then? you can take a sum, for example, and manipulate the sum to select the instance of the sum whose projection on a plane gives the best fit when it's compared to the target image of the patient. So you assume that that one is the actual anatomy of the patient. So that leads to the aim of my PhD project, which was to develop and validate a subject-specific finite element procedure which could predict the mechanical behavior of human femurs while starting from a single DEXA image. So to fulfill this aim, I tried to follow this flowchart during my PhD studies, where the three starting points were the mechanical test, which were used as a basis to validate the predictions from the finite element models. And then CT-based finite element models were built, and which represented the state of the art in terms of how accurate can a finite element model be for this sample, and the sum, which was used to reconstruct the 3D shape of human femurs starting from a single DEXA image. The material used in this thesis consisted of 6 composite bones, for which we had CT images and experimental measurements were available from a previous study. And we had instead 3 human bones onto which the actual tests were performed, coming from 3 male donors from Finland, age ranging between 22 and 58 years old. And for each of these 3 femurs, we had images from CT scans, as well as 2 different DEXA devices, iDEXA and Prodigy from GE, where iDEXA is a newer device with a high image resolution. So the first step in the project was to make the mechanical test. And when performing mechanical test, one of the first questions that we should address is what do we want to measure and how are we going to get those measurements? So other than the force displacement curves, which are recorded in pretty much all the mechanical tests performed, usually we like to measure the deformation of the specimen during the test. And you can do this by adopting different techniques, some of which are discrete and contact-based, like strain gauges or fiber Bragg grating sensors, or some other that allow to reconstruct the full field strain distribution, like digital image correlation and digital volume correlation. So at the moment, strain gauges are still considered to be the gold standard when it comes to measuring deformation on bone, and that's because they are very well established, they know to be accurate, we know well how to attach them to the bone. But if you also look at the program of this conference, you will see that full field measurements have been used more and more in the last years, and that's mostly because you can get way more measurements than what you can get with strain gauges. So we decided to use digital image correlation in our experiments. And for those of you who don't know, the concept behind digital image correlation is in a way quite simple. So if you have your specimen under test, then you use 1 or 2 cameras, or theoretically even more than 2, to record a certain surface of the bone. And what you do is that you typically paint your sample with a white background and a black randomly distributed speckle pattern. And you perform your test. After that, you take your images and you try to track the displacement of each of these black speckles across consecutive frames. And what you end up with is a matrix of displacement, essentially, which if you take the derivative, you can get the matrix of the deformation for that surface that was tracked by the cameras. And that's an example of what you can get. That refers to the major principal strain of one of the bones in our sample, very close to fracture, I would say. So that's a picture of the mechanical test. To perform this test, I went to Delft in the Netherlands, to the Technical University. So what we did was that we placed a bone under the universal testing machine, and we had 2 cameras to record the experiment. In this experiment, the distal part of the femur was fully constrained, whereas we apply compressive load on the femoral head until a macroscopic fracture could be spotted. And we were recording the experiment at 3,000 frames per second, while we were compressing at the control displacement rate of 15 millimeters per second. And as a result, we got the force displacement curves that you can see on the left-hand side, right-hand side of the slide. So after the test, we performed digital image correlation, which actually proved to be a harder task than we thought at the beginning. there is a lot of parameters, and you have to keep control of a few things. So after playing a bit with the parameters, we ended up choosing a subset size of 25 times 25 pixel, which physically corresponds to the size of the yellow squares in the picture. And then we also realized that there was noise in the measurements, not surprisingly. So what we did is that we placed an aluminum plate alongside the bone, and that plate was basically not deformed during the test, since no force was applied, but was moving alongside the bone. So we used that plate to check what are the noise levels in the measurements. And in order to reduce the noise, we applied a 100 Hertz low-pass filter on the displacements before we derived the strains. And as a final result, we obtained about 10,000 measurements per bone. So here I'm showing just a few results of what you can extract from these measurements. So at first, what we did was to define 3 virtual strain gauges on the head, neck, and diaphysis level. And we extracted the major and minor principal strains from that regions, which was essentially a way to make a qualitative comparison between the measurement that you get from digital image correlation against what you normally get using strain gauges. So we were essentially comparing previous studies performed in a similar way that used strain gauges instead. Whereas on the right-hand side, we can see the pattern of the major principal strain, at least for the moment when the crack opens for specimen number 2. And here again, we can see what happens with digital image correlation when you try to map the deformation at the moment when the crack appears for specimen number 2 and specimen number 3 in our sample. So at that stage of the project, we ended up having a lot of measurements, essentially, just a lot of data. We got some nice clue, but then the next step was to build finite element models based on CT images and then match those predictions with the experiments. So here, the first question we had was, how are we going to compare the measurements, the predictions from the finite element models, to the measurements we got from the experiments? Since now we had thousands of points that has to be compared. So in order to address just this issue, we took 6 composite bones, which are quite easy to model. We had the CT scan, so we could reconstruct the shape. We know the material properties because we know them from the manufacturer. And so we built finite element models that we could trust in a way. And then we had the set of mechanical measurements that were taken by Sami Vanhanen at University of Eastern Finland, where he used digital image correlation to get the strain pattern for these composite bones. So then we thought about how to perform the validation, and what we did was, first of all, to register the point cloud from digital image correlation over the anatomy of the bone, of the composite bone, and then for each surface element of the finite element model, we defined the smallest sphere that circumscribed the element, and we ran the validation by selecting the experimental points that were inside the sphere, and we compared the average value of these points to the strain predicted by that element. When you iterate these for all the elements, what you can do is that you can perform a linear regression analysis, and as you see in the result on the right-hand side, when we compare the predicted strains versus the measured strains, we got a coefficient of determination above 0.9, a slope close to 1, and the root mean square error, which was quite low. So we thought, well, this type of validation might work, plus we saw that the registration errors were very low between the DIC cloud and the model, so we used this validation approach for the rest of this PhD project. So then it was time to build the finite element models. So here again, it's a quite consolidated procedure. So we used the approach where you take the CT stack, you segment each slice of the CT stack, you extract the shape. After this, we performed reverse engineering, where we also added the distal pot that was constraining the bone during the experiment. And finally, we meshed the shape using second-order tetrahedral elements. And at last, we mapped the material properties. Here again, we used inhomogeneous isotropic material properties, where we map the Young's modulus on each element based on the underlying CT values and the law that links the apparent density of bone to the Young's modulus. But then we had to predict also how the bone fractures. So we had to think about the material model and the way the bone fractures. So what we did is that we came up with a quite simple material model with different strain limit values for tension and compression and for yield and failure. So what we had is that we took yield strain limit values from a study from Bayraktar and co-authors in 2004, and then we took ultimate strain values from an older study from Riley from the mid-70s. And we did a material model in which whenever an element is reaching the yield point, its modulus is reduced to 5.5% of the original modulus. You continue the simulation, and whenever the first element is reaching the failed state, the whole model is considered to be failed. So that was relatively simple. Plus, we introduced a strain rate correction factor, which basically accounts for the bone getting stiffer when you compress it at higher strain rates. So if we think of the modulus of the bone as given by the reference modulus times the strain rate correction factor, then the reference modulus is given by the empirical law that links the modulus to the apparent density, and the strain rate correction factor is basically making the bone slightly stiffer when the strain rate is high, using a power law to the power of 0.06, which was first proposed by Carter and Hayes at mid-70s. So when we use this type of modeling approach, we performed our simulations and we validated our results. So what we obtained for the 3 bones in our sample, when we compare the principal strains at the load of 4 times the body weight for each patient, we obtained a coefficient of determination which was well above 0.9 for all the 3 femurs and for the pooled result as well. Slope and intercept were close to unity and 1, and the normalized root mean square error was about 10%. So we were quite happy with these results, since these results they pretty much match all the previous published studies that were available in the literature, with the significant difference that this time the validation was performed against thousands of measurements coming from digital image correlation and not from 15 to 20 data points available with string gauges. So this was, of course, not the end of the study, since we wanted to predict the strength of the bone. And so we did. So with the material model and the fracture criterion that we developed, we were able to predict the femoral strength with an error below 2% for bone number 1 and bone number 2, whereas we could not validate bone number 3 because there was a problem in the experiment slightly before the fracture occurred, and so we could not validate that bone. So even though we have only 2 bones, we were quite happy with this result. Plus, we could see that the predicted fracture origin point was quite close to the experimental fracture rim, where the black line is the experimental fracture rim, and the red points are where the model predicted the fracture to start. Then the model is not implementing any crack propagation, so that's where the model stops in this case. So at this point of the project, we had the mechanical test done. We had CT-based model which performed fairly well against these experimental measurements. So then the last part was to take this statistical shape and appearance model, use it to reconstruct femoral anatomy starting from a single DEXA, and see how well can these perform. So we validate everything against experimental measurements, and then we can compare against the CT-based model and see who performs best. So here the goal was not only to see how well these can perform, but also what are the single components of this sum-based approach that affect the final accuracy. So we built 3 types of models. One that we call sum-based BMD models, in which the shape of the model was taken from the CT images, but the material properties were reconstructed from the DEXA images. The sum-based shape models, in which it was the other way around. And last, the sum-based shape and BMD models, in which both the shape and the material properties were reconstructed from the single DEXA image. And we also did this for 3 different types of target DEXA images, where one target DEXA image was what we call CT projection. So we basically obtain a DEXA image by projecting the CT volume over the anteroposterior plane, and that image represents a sort of optimum in terms of signal-to-noise ratio. And then we had the 2 DEXA images from the DEXA devices, iDEXA and Prodigy. And so we built basically 3 models times 3 target images, and we validate everything against the measurements. So a first control we did was to check how good was the sum in reconstructing the shape. And you can see the point-to-surface reconstruction error on the left-hand side, while on the right-hand side, we have the volumetric difference for the reconstructed shapes limited to the neck region, since that's the region where you are most likely to experience a fracture. So that's the most critical one. So what we can see from here is that the models that adopted CT projection as a target images were on average more accurate in reconstructing the shape compared to IDEXA and Prodigy. And that was no surprise since, again, CT projection has a higher signal-to-noise content. And then we moved on and we validated how well this model performed in predicting the mechanical behavior of bone. So on the left-hand side, we have the linear regression analysis between the major and minor principal strains for the sum-based shape and BMD models. So when we reconstruct completely the bone from a DEXA image and we try to predict the strains, we get a coefficient of determination between 0.87 and 0.92, and that depends on which target image you use, and the normalized root mean square error between 9 and 12%. And that was quite good, since we can consider this just to be a mild decrease with respect to the performance of the CT-based finite element model. So we tried to predict also the femoral strength, and here we had slightly higher errors instead, with an error of 6% for bone number 1, and an error of 19% for bone number 2. And in general, depending on which model you build and which target image you use, you might have errors up to 20%. And then, since we had a lot of models, we also tried to observe a couple of trends. The first one was that the models that use CT projection to reconstruct the shape were on average more accurate than those implementing IDEXA and Prodigy. And again, CT projection has a higher signal-to-noise content. What it was more interesting to observe is that IDEXA is a 10 years younger device compared to Prodigy with a much higher image resolution. But despite that, the performance between using IDEXA and Prodigy were quite similar. So it's probably not the resolution, but the actual signal-to-noise ratio, the parameter we should look after when building these models. And the second trend was that, on average, the model that implemented the reconstructed shape performed better than those implementing only the reconstructed set of material properties. And although we need to check a few more things about this type of result seems to suggest that at the moment we should focus on improving the reconstruction of the material properties. Of course, we had a few limitations in this thesis. The first one certainly being the small sample size, since we had only 3 cadaver bones available, and those who work with cadaver bones, I guess they know how complicated it might be to get hold of these precious samples. Anyway, we would like to overcome this limitation in the future by collecting new femoral anatomies, which we already did, and we would like to test them in a new loading configuration, which is fall to the side. So we compensate for the small sample size, plus we compensate for the fact that we only have one single loading direction tested at the moment. A second limitation was that we were not able to localize where the fracture starts during the experiment. And this is due to the fact that, well, first, if you look at these frames in the picture, there is like 0.3 milliseconds difference between these frames, and still there is no crack at the 0 image, and in the frame after that, the crack almost propagated all the way through the femoral neck. So even though we recorded 3,000 frames per second, that was not fast enough. But the other reason was also that we were recording the anterior side of the bone, whereas for this type of loading condition, it is likely that the fracture originates either on the lateral side of the neck or on the medial side of the femoral neck. So I suggest that future experimental studies, if possible, might adopt a configuration like this one, where you have one pair of cameras tracking the medial side of the neck and the other pair tracking the lateral side of the femoral neck. So if you can get 4 cameras and measure the strains using digital image correlation and synchronize at all time, then you can maybe get a better description of the strain levels at the bone when the fracture originates. A third limitation, which is actually more of a discussion point, I would say, is that after I did this experiment, I quickly realized that digital image correlation comes with a huge amount of data. It's really thousands of points per thousands of frames per many bones. It's a lot. And despite I tried different ways during my thesis to make use of this data, from plotting the principal strain magnitudes to plotting the principal strain directions, strain limit plots, etc. Still, most of the data that I acquired went unused, or at least it went unpublished. And in a way, I feel it's a pity. I guess there would be many experiments like this done that had the same outcome. So I admit I don't know much about this, but I feel we should find a way to upload this data in some safe place where you can preserve the authorship right, but still make it available for other people to have fun with them if they want. And that's, I think, a good discussion point about how to share this data in a safe way. Here I'm just listing a few platforms that I know they exist. Biomed Town, which we use in Bologna, SimTK, and others. So to conclude a bit about the findings in my PhD studies, the first major finding was that it's possible to use digital image correlation to validate the finite element predictions in a quantitative way, which might sound obvious, but at the time when the experiment was performed, to the best of my knowledge, there was no study doing that before. And we also show that we can reduce the noise in the DSE measurements, where it's very important, first of all, to track the noise in DSE measurements, because they can be very noisy. And you can reduce it by using a simple filter on the displacement before deriving the strains. And what we also notice is that our bones behaved overall linear elastic since they were loaded at physiological strain rates. And this was already observed in previous studies, but this time we have thousands of measurements from digital image correlation that sort of corroborate this observation. A second finding was that the city-based finite element model were able to predict both the principal strains and the femoral strength with great accuracy. And so we use these results as a gold standard to see how well can we predict the strength using reconstructed models instead. And at last, these finite element models that implement a reconstructed anatomy from a single DEXA image, they were able to predict the strains fairly well and the strength with a bit higher error. But nevertheless, we should not forget two important points. The first one is that this type of modeling approach can be more easily implemented in a current clinical scenario, because what you need is simply a two-dimensional DEXA image, which you already have in the current screening. And the second fact is that if you're able to reconstruct the 3D anatomy of a bone starting from a two-dimensional image, then you're also able to test different loading conditions at the same time using finite element models. And this is known to increase the ability of finite element models to separate between fracture cases and controls in cohort studies, for example. So if we now think about how are we going to transfer not exactly this approach, but these types of approach to the clinical application, I think that at the stage where we are now, at least for our project, we need to test the framework under different loading configurations. We also would like to expand the size of the training set for the statistical shape and appearance model, where this can, for example, allow us to, for example, build different sums that could be a sum for each specific population group, a sum for men and a sum for women, and see how that affects the accuracy of the reconstruction. In a more long-term perspective, I think the biggest challenge is to go from predicting femoral strength to predicting the risk of fracture, which is not an easy task, of course. And we also would like to see how robust is this approach when we test it against multiple clinical cohorts and not just against cadaver femurs. And a very important point is also that this technology, in the end, should come at a competitive cost for the healthcare system and should have a competitive execution time, where nowadays a decision about the fracture risk is taken in about half an hour in the clinics. So here I just elaborate a bit more about how to go from strength to fracture risk. So again, one loading condition is not enough, as it was showed already by Falcinelli and co-authors in 2014. So if you use finite element models and predict the strength in different loading conditions, we get a much better prediction of who is going to fracture and who is not, at least in small clinical cohorts and in retrospective studies. So what we are trying to do right now is to perform mechanical tests in a configuration resembling a fall to the side, where we want to use two cameras to track the deformation on the medial side of the femoral neck. And at last, I am borrowing this picture from a nice perspective paper that I recently read from Hernandez and van der Molen, which was published on JBMR. And what this image, which I took from their nice paper, says is that when we consider the mechanical failure of bone, this can be due to a single large load, where in this case we are referring to the elderly population. So single large load means a fall from a standard height. Then it's the femoral strength, the parameter we should look after. But fracture can also occur as a result of a modest load, which can be, for example, carrying a child, carrying some weight, etc. And in this case, it's more the fracture toughness, the parameter we should look at. And if we take an even broader perspective and we look, for example, at fracturing the spine, this might be the result of repeated cyclic loading and damage accumulation. And in that case, it's fatigue strength what we should look after. And this is just to say that I believe that one of the advantages of using computational models, such as finite element models, is not just that we should try to replace BMD in order to predict the femoral strength, but we could take advantage of the fact that once you have these models, you can predict way more things than just the femoral strength. And those are things that BMD does not correlate with. So I think that could be one interesting key to further develop this type of model. And let me conclude by acknowledging the people that helped me during this PhD thesis, starting from my two supervisors, Hanna Isaksson and Matti Ristima from Lund University, and then the people that helped me during these studies. So we have Jukka and Sami from University of Eastern Finland, and then I have Harry, Saber, and Namir from the Technical University of Delft in the Netherlands. And I think I should acknowledge all the funding sources I got during the thesis, because they made my life so much easier in the end. And this is just a cover page of my thesis. If you're interested, you can find it online. And I actually also have a bunch of printed copies left on my shelf. So if you like, just drop me an email. I will send you one. Thank you for your attention.
So Lorenzo, thank you very much for this very nice presentation on an extremely relevant topic, clinically and also scientifically. So yes, question, please.
Yeah.
Congratulations on your nice work. I'm not very familiar with the experimental methods that you used. Did you distinguish cortical and trabecular bone in your model?
No, so what digital image correlation can do is only to track the surface, since you basically have a camera. So what you see is just a deformation at the surface of the bone, while you of course have cortical bone.
The density Young's modulus relationship that you used is also...
Okay, for the models. So you mean...
Yeah, models, yeah.
This one.
Yeah, you said you did use the Young's modulus according to some image data, I believe.
Yeah.
Right? So that was also valid for the surface of the femur.
Yeah, so we use the same law for cortical and trabecular bone.
And did you simulate the crack propagation? So when a part of the bone fails, you simply removed it from the mesh? That's how you simulated it?
No, so in this implementation, we actually just implement yield, and then the fracture, the simulation goes on. And then once the first element fails, we assume that everything is broken. So we assume that the crack is going to propagate very quickly, as that's what happened in the experiment. So we are not really interested in modeling the crack propagation at the moment. That's actually something we are working on and would like to implement in the future, some more advanced way to model the crack propagation.
One note, the yield criteria that you used by Bayraktar, I think it's more valid for trabecular bone.
That's valid for trabecular bone. Those data, they actually refer to trabecular bone. However, we use that type of yield limit values also in previous studies. It has been used to predict the fracture at all levels, and it proved to correlate very well with the femoral strength in the end, both in side fall and in single leg stance. So we trust it, even though it comes from trabecular bone, we trust it enough.
Okay, thank you.
Here up. Maybe you can start. Yeah.
Thank you for the nice talk. So actually, I'm happy to see that you also visited to Delft. So I want to ask you one question related to statistical shape model. So if I understood correctly, you say that you are using one weave DEXA scan and then you reconstruct the 3D model. So how did it occur? Because you say that you project the CT scan, but with one weave, how it could be possible for you?
Okay, so just let's see if I have an additional slide with slightly more details, which can help. So yeah, so the reconstruction part is what you see in the bottom part of the slide. So what you do is that you take an instance of the sum and you create this digital reconstructed radiograph. So it's like you simulate a radiograph over that sum, so you get a 2D image, and then you compare the 2D image you generated to your DEXA image. You see how well they match. And then, I mean, there we are minimizing the sum of the absolute differences between these two images. So if it's converts your optimization process, then you take that 3D shape as your shape. If not, you iterate and you keep modifying the sum, create a new reconstructed radiograph, recompare, go back until.
Yeah, thanks for the explanation and also for clinical implementation of those models. So for how long it takes to reconstruct 3D model? Because you say that in clinical practice they take almost half an hour to predict the fracture. With these kind of models, how long does it take?
So at the moment, the reconstruction of the bone takes hours, 1-2 hours, just to reconstruct. Then you have to build the model, run them. So overall, it still takes too long.
Yeah.
We can make it much faster because it's all MATLAB implemented. As for example, like the finite element models they have, they print a bunch of debugging codes, which I could avoid. But still, we are not getting to 30 minutes with this implementation, so we need to work on that.
Yeah, okay, thank you.
Yep.
Thank you very much, Lorenzo, for this great talk. I have 2 comments, maybe then questions. The first one is a compliment, because whoever's tried to do this experimental numerical work knows what it takes to go into the depth and do it properly. So this is a great achievement done in a single PhD, so this is great. The second one is, I think you're missing one more thing to accomplish the work, and this is, in the beginning you showed, or you made a statement, FE is better than DEXA, and I tend to agree, but my question would be, is DEXA-based FE better than DEXA? So this is something you would have to add to convince the clinicians and explain them why they have to install a separate computer in their room and let it work for hours for a single case while they could get their DEXA values in seconds.
Yeah, thanks for both the comments.
Yep, Enrico, over there.
You hear me? Yeah. So I just keep congratulating because it's a lot of work. So thanks a lot for this presentation, Lorenzo. I have a question about your correlations when you compare the output of the models and the DIC. In average, works pretty well, but if you look at the maximum error, they go up to 80% in some cases. So I was just wondering whether you checked where those errors are, and in particular, considering that you have a single element failure criterion, it may affect then the prediction of the strength.
Yep. So I don't think I have any specific slide in here, but yes, we did check where this error come from, and we were in a way happy to see. Let's see if I have an image that helps. Yeah, maybe something like this. So yeah, usually the biggest error, they are on the border of the DIC cloud, and that's, I believe, a problem of the correlation thing. So in a way, they were reasonably far from